Hi everybody, I'm Gary Watson. Welcome to Issues. This week we're talking to my good friend Rick Kissing, and we're talking about space travel, the Mars rover, a whole lot of things to do with technology. Welcome along, Rick.
Thanks, Gary.
Well, Rick and I first met through a mutual hobby of amateur radio, didn't we?
We did.
We first caught up, and then
yeah, great hobby.
Yeah, and we've had lunch and talked technology and all the other things that people do. So yeah. Now you were involved with the software that guided one of the earlier Mars rovers to Mars.
That's correct.
Can you tell us a little bit about what got you involved in all this technology?
Sure. I was a software consultant in Silicon Valley for probably 20 years. And one of my clients during that time, and this is probably the early 80s, something like that, was Lawrence Livermore National Laboratory in California. And as part of the work that I did there, we developed spacecraft components, for miniaturized spacecraft components. And so one of these components in particular was a small, lightweight star tracker and star camera. So I helped to commercialize that technology, and in the process it was used on around a half a dozen or so different space missions, including 3 to Mars, one of which was the rover.
And with this technology, Ray, like when you're out in space, you've got no magnetic fields to go by, you've got no GPS. Right. So is this like a three-dimensional star navigation system?
Yes. So the software is called the Stellar Compass, and the reason I named it that is because it serves a similar purpose to what a magnetic compass does on the Earth, in that when you're up in space, as you said, since you don't have a magnetic field, it helps you measure and determine where you're pointed, where the spacecraft is pointed. And the reference system, instead of being the magnetic north and south like it is on Earth, is the star field around you.
Right. Now, would that make it fairly accurate, because the stars are there when you're out in space 24/7, aren't they?
They are. Now the accuracy varies depending on the instrument. There are some special purpose star tracker type cameras that they use in say geosynchronous orbit or something like that have very high magnification, narrow field of view, and they can very accurately track where they're pointed. For the missions to Mars, the main purpose of the software was to guide the flight from after it left Earth orbit, after the vehicles left Earth orbit, to the time that they entered Mars orbit. So for that period, generally for these spacecraft, they didn't need a lot of accuracy. They need some accuracy. So there were trade-offs in the design of the system along those lines.
Now, going from the Earth to getting into the Mars orbit, what kind of tolerances are we talking here? Are we talking plus or minus 10 kilometers, or what kind of margin of error was there?
Well, they measure tolerance in a couple of ways. One is an angular radiant tolerance, which is what you're looking at on the way there, and that's might be in terms of milliradians. Is kind of the metric that they use, and that's just how accurately you're pointed with respect to the stars. And that's important because when you fire your engines to correct your path on the way there, you want to make sure that you're firing them in exactly the right way. Then the goal is that once you end up at your destination, that you're within a certain narrow window, so that you can properly enter orbit around the destination planet, or Mars in this case. And so that number is then measured in kilometers.
Now, when the spacecraft is traveling towards Mars, is it being influenced by the gravitational pull of like the Moon and other planets?
It's mostly, yes it is. It's influenced particularly by the Sun, of course, since it's a major gravitational influence on everything in the solar system. But it's also influenced by the Earth and by Mars and by Jupiter. And so the gravitational pull of those planets is important and is something that needs to be factored into the flight calculations along the way.
Okay. So the software you wrote, was that controlling rockets or jets that would make the correction?
It provided inputs to the control systems that were used to fire the jets. So before you can fire a jet, you first have to know where you're pointed with respect to your destination and the other things in your environment. And so, and you also need to know what time it is. So the purpose of my software was to provide that attitude information.
Right.
Yeah.
Big responsibility, because the whole mission could have fallen over if you got something wrong.
Yes.
You know,
Yes,
one line
quite
of code.
Yes, absolutely. And equally bad, if something goes wrong, you can't just reach out there and fix it.
Yeah.
You can't just call it up and say hey, I made a mistake. Push the reset switch.
Right.
It doesn't work that way.
So you couldn't call them up or email the astronauts and say, hey, look, I've got a software upgrade for you.
Yeah, no way.
It's all going to fall over in a few minutes, so I need to.
So yeah, reliability is a huge huge part of this. We did a tremendous amount of testing for that reason. Yeah.
Now, did you have software or have a means of monitoring that software the whole time, the telemetry data coming back from the spacecraft, so you could keep an eye on what your software was doing?
Well, as a contractor, of course, I'm a little bit removed from the day-to-day operations once the spacecraft is launched. But I was in regular touch with the people at Mission Control, and they did have a way to take images that were captured by the star cameras. There's actually, most of these vehicles had 2 star cameras on board. Take those images and send them back to Earth, and then we could look at and analyze what was happening in those images. So you can see, lots of cool stuff from pictures that are taken in space that they have a certain character to them that you just can't duplicate on Earth. I know this in part just from first-hand experience, because we took a lot of pictures of the stars from Earth, from the ground, and they look much different.
Right. Exciting where this technology is all going. Can you see that we are making some major advances? But because when Kennedy made the promise of putting man on the moon, there seemed to be an awful amount of development and resources went in, and then it seemed to sort of plateau a little bit after that.
Yeah.
Where do you think we're at now?
Well, so certainly that's true in terms of the space programs, the manned space in particular. I mean, the computers that were used to send man to the moon were what you'd find today in a calculator or something. I mean, they're very weak. Even the space shuttle, the computers were very primitive compared to what we have today. So yeah, technology has advanced tremendously. Back when we originally began development on these star cameras, just the idea of a CCD type camera, which is something we see now every day in handheld devices, was very new and very innovative back then. This was, maybe around 1990 or something like that. So just in that time period, it's advanced now to the point where it's an everyday thing. I mean, I've got one on the phone in my pocket. It's advancing tremendously with miniaturization, cost reduction, improved density. Some of those things, unfortunately, work against you in space, by the way.
Yeah, and some of the forces, like the takeoff, seems to be a pretty aggressive kind of climb into space.
Yeah.
And what about radiation? Is that a factor?
So, so both of those things, the vibration issues, the mechanical shock issues, are substantial during launch. Not so bad, while you're en route. But what does get you en route is the radiation, mostly from the sun, although there's also intergalactic radiation gamma rays and so on. And we can actually see this on these images that we take. So you take an image of the stars, and it normally has a fairly black field, but there'll be lots of little white specks on it. And this is actually from little elements of radiation, little protons that are hitting that CCD and making a little light mark on it. So it's interesting in these cameras that we can actually see that. But the computers and so on, you don't see it, but what can happen is those same protons, if they hit a transistor inside a computer CPU, can cause it to shut down, stop, turn off. So the computer hardware has to be radiation hardened in a certain way to make it last.
Did you have to write, as part of the software to control the spacecraft, did you have to write any software that for when things go wrong? of all the possible things that could go wrong, you had a kind of alternative.
So in my software, yes, there's certainly failure modes, but my software is really just it's a measurement kind of a tool. So there were software layers below mine that would deal with mechanical failures, like let's say of the servos, or the thrusters, or any of the other myriad of devices on the vehicle. For me, I just had to deal with things like a camera failure. What happens if the image comes back and it's all black, or it's all white, or hugely noisy from some radiation storm or something like that.
So you didn't have a screen for the astronauts of please reboot Windows now or anything?
No,
okay.
Nothing like that.
Okay, so this is basically taking lots of pictures, analysing the distance between known points, and then working out the calculation between the different pictures. Is that?
Yeah, that's pretty much it. Yeah, it's so what the software does is it takes a picture of the stars, and it can have other artifacts in it, like there's a number of them that I have with Mars, strikingly right in the middle of the picture, for example. And then what it does is it draws digital triangles between the stars, and then takes those triangles and matches them against an onboard database of patterns, and tries to rotate one into the other. So by doing this sort of fancy pattern matching and math thing, you can figure out where in the sky you're looking.
So this is like advanced algebra, where you're taking some knowns and using that to generate the unknown.
Yeah, that's right.
In a nutshell, I suppose.
In a nutshell.
Okay.
Mm-hmm.
Now, what were some of the other technologies that you were involved with associated with that?
With the Mars stuff, well, so there's a lot of effort went into the development and test side. So there's a big kind of software development and ground-based aspect to it. We did things like take the cameras out under the night sky and let the Earth rotate under the stars, and capture thousands upon thousands of images. And there's a whole set of software that's required to analyze those images, and to also to develop the database of stars. Turns out that measuring star positions accurately from the ground is a very difficult thing. So we used earlier space-based measurements of stars to build up our catalog. And there's also a whole variety of mathematical corrections that you have to factor in. It's things like when spacecraft move quickly through stars, it turns out that their position in the sky changes slightly. And things like that had to help.
Did you have problems with things like the Doppler effect and various other effects from the visual aspect of this?
Yeah, not Doppler specifically, but similar types things. Yes,
right.
That's right.
Where things change when the distance changes.
Yes, that's right. Change as your speed and direction change.
Now, you spoke before about gravity. And it's something, of course, there's been all sorts of scholars and scientists define. How would you define gravity?
Well, so the way I look at gravity a little bit differently, I think, than a scientist. I'm more of a physicist and computer scientist, and so I have a model of gravity that I found to be very useful. And it works like this. Imagine yourself standing on the surface of the Earth, but the Earth itself has been condensed from the giant thing that it is down into a microscopic invisible dot. But it still has the same mass. And so you're still standing at the same place, but the whole Earth has been shrunk down to this invisible dot. Now let's say you have a ball, it doesn't really matter what it is, in your hand, and you just let go of it. You think about what happens now. It's basically going to be the same thing that you see on the surface of the Earth, that it's going to fall. But now, since there's no surface of the Earth there, it's just going to keep falling, and it's going to go faster and faster and faster until it hits where the center of the Earth is, and then it's going to keep going all the way to the other side, about the same distance away. It's going to stop, and then it's going to come back, and it'll land right back in your hand. So we'll have traveled this giant distance and gone extremely fast when it gets close to the center of the Earth, and it comes right back to you. Now, if you just throw it just a little bit, it'll do the same thing, but it'll make a little bit of an ellipse, a little bit of an ellipse. It's not a circle; it's an ellipse. So then, the harder you throw it, the wider that ellipse gets. And so now you can imagine slowly that the Earth is coming back into the picture, back into the view. Now you can see you actually have to throw it quite hard for it to not hit the surface of the Earth. Let's say there was no air, right? You have to throw it quite hard. So this is how orbits work. Because it's really what's happening is this space vehicle is moving so fast that it's just always falling. It's just falling right around the Earth, coming right back around.
So this is the principle of Earth-orbiting satellites.
That's right.
Where they are set at just the correct point to keep them there.
That's right.
But they still have to use propellants on the geostationary ones to keep them in respect to the Earth, don't they?
That's
Why
right.
is that?
That's right. Well, what happens is that these orbits are not all orbits are perfectly stable. So there's a lot of other, the Earth is not a perfect sphere. There's mountains, and it's bigger in the middle than it is at the poles, and also for lower orbits, the atmosphere actually extends up and can interfere. There's the moon also is another big mass out there that's kind of pulling and tugging. So things are not quite as simple as our little perfect world model. So things move around a little bit, and eventually you need to apply a little bit of thrust to make a correction.
Right. Is this like when the satellite is round the opposite side of the Earth to, say, the Earth and the sun, the moon and the sun? That the moment it now gets exposed to now the Earth and the sun again, that its gravity is going to change slightly? Is that a factor?
What happens is that the moon and the Earth and the sun are all tugging on that. They each have these little gravity wells, these little areas where things want to fall into. And so those little tugging motions as the vehicle moves around the Earth, or as it moves, say, from the Earth to Mars, for example, all this pulling and tugging is happening. And we can now, our gravity models are good enough that we can pretty accurately take all of that kind of thing into account. But there is still drift that happens.
Right. We're talking technology, we're talking space communication, space travel with Rick Kissing, and we're going to take a short break. Back shortly.
O2B Healthy.
Lifestyle, diet and exercise, complemented with quality supplements, can provide you the insurance vital for your natural health and well-being. With over 10 years professional experience making some of New Zealand's most trusted nutritional supplement brands, visit the O2B Healthy Factory Outlet in Wakatu Industrial Estate. Over 200 supplements to choose from, free on-site parking, no middleman.
O2B Healthy. Caring for you naturally.
The majority of information in our life comes to us through our vision. With only one set of eyes to last our lifetime, it's important that you look after them. For over 20 years, Physique Harrington Eye Care has led the way in providing the Nelson Tasman region with professional eye care. Our team are committed to providing you and your family with the highest standard of eye care. As part of this commitment, at Physique Harrington Eye Care, we recommend Crizal lenses. Crizal is a revolutionary lens which repels dust and fingerprints. This means it's easier to clean and stays cleaner longer. Visit us at our Nelson, Richmond practices and ask about our Crizal satisfaction guarantee.
Why would you want to pay as much as $1,000 for a single bed mattress when you can buy a high quality locally made mattress like this for as little as $220? And a queen size mattress could cost you in excess of $3,000, but at Nelson Beds you could have a mattress like this as low as $425. So why would you go out and spend a fortune on your child's bedroom when you can come to Nelson Beds and buy a complete single mattress and base set, a 7-drawer Scotch chest, a headboard and a 3-drawer bedside cabinet for as little as $979? So call and discuss our custom manufacturing options and local after sales service at Nelson Beds, Nelson's only bedding manufacturer.
Discover the Belgrove Tavern just 20 minutes south of Richmond on State Highway 6 for meals, functions, weddings, barbecues and garden bar with lots of room for kids. Come and see us.
Welcome back. You're watching Issues. My guest today is Rick Kissing, and he has been involved in the writing of software that has got some of our spacecrafts to Mars and various other technologies. Tell me, Rick, one of the things that I'm always sort of worried about, and a lot of folks are, is the space junk that is accumulating up there. Is it like we've got a whole bunch of mechanics that are sort of arriving up there and being untidy with their tools, and there's nuts and bolts flying around everywhere and all sorts? Is it a little bit like that?
It is a little bit like that. But the thing to keep in mind is that space is a very big place. And so, you know, you can imagine a bolt, you know, flying across the Pacific Ocean. I mean, it's very unlikely that it's going to run into anything.
Right.
So there is space junk up there, and you do have to be conscious of it. And some of it is tracked by the United States Space Command. And you know, it's important to know where the bigger pieces are. The good news about most of that stuff is that because it doesn't have a little engine on it to keep it you know, in the right place, those orbits tend to decay. You know, all of those little pieces of junk, they're all actually in orbit, just like a satellite is, and so those orbits tend to decay, and that material tends to fall to Earth.
So if we're looking at it at night and we see it like looks like a flying star, it could actually be a piece of, well, it could be bits of space junk, or it could be something else. But
absolutely, yeah. I mean, in addition to the man-made junk, there's also natural junk up there. There's a lot of natural dust, and the Earth flies through these giant fields of comet debris all the time, and you know, that's far more junk than any human has introduced.
There's one comes about. There's a whole group of them come, but there's quite a significant one about November each year.
Yeah, there's a few of these the big star showers, you know, that are caused by the Earth flying through a field of comet debris.
And then they start worrying about some of the geostationary satellites being affected by this, don't they?
Yeah, yeah.
Okay.
Yeah, but again, the material is not very dense, so it's very unlikely that any satellite would be hit. The much bigger risk up there for spacecraft is actually the sun, and radiation storms from the sun.
Right, okay. Space travel in general. We seem to be at a bit of a lull at the moment.
Yeah.
We've had the shuttle project has ceased.
Yep.
There are rockets putting satellites into orbit all the time, but in terms of a space project, we seem to be going backwards now.
Yeah,
where do you think it's going?
Well, you know, my opinion on this is perhaps a little controversial. I'm in the camp that believes that the huge investment in the International Space Station and in manned space flight in general, although, you know, very interesting, I suppose, from a just a science and perspective and all that, was just a huge waste of time, money, and effort, and that resources would be much better expended on robotic type missions of the type that we're now doing on Mars with the rover and so on. We just learn so much more with no risk of human life compared to you know, these other missions at far less cost, far better science. I'm all for manned exploration in the long run, but I think we have a lot to learn. What I'd like to see when man does really return to space is not to just go to orbit around the Earth, but to actually have a colony somewhere, you know, say on the moon.
One of the big problems is, of course, all the distances involved. Like to our nearest star, it's something like 4 million light years or something crazy.
Yeah, 4 light years.
Yeah, 4 light years, is it? Yeah, which is a incomprehensible kind of.
It is. It's a huge distance.
Yeah.
Yeah.
So we're not going to be able to really do anything to communicate. I mean, even if there was someone there that could say hello back, it's really hello, and then 8 years later, it's 4 years to get there, and another 4 years to get the answer. So
yeah, absolutely. Interstellar travel is just a huge technical challenge. You know, it's something I think that would be great to strive for. But you know, what I'd love to see is a robotic mission first. And you know.
Okay. Because you don't have to build in systems to keep oxygen and food and all the other things, do you?
One of the biggest single costs in sending anything into space is geometrically proportional to mass. So the smaller you can make something, it just gets hugely cheaper. Any sort of big thing that's, you know, I mean, it's a mistake, I think, to think of spacecraft as being like airplanes. You know, airplanes get a lot of their fuel out of the air. They pull all this oxygen out of the air. Spacecraft have to take their oxygen with them, And so as a result, you have this very tiny little vehicle, with this huge thing of fuel on the back of it. So yeah, smaller is way better. Can do and see a lot more.
Do you think there is new technologies that will be able to replace this conventional system?
I do.
Of using like very high impedance magnetic fields to actually utilize the gravitational pulls already out there?
I do think we're seeing some advances now in spacecraft propulsion, things like ion engines, for example. A lot of potential in that area for sure. Absolutely. Yeah. Chemical propulsion, which is the main thing that we've been using to date, is unfortunately very inefficient.
Right.
Yeah.
Okay. Now, with all these technologies, I guess there comes a cost. This developing all this kind of software. How many people were involved in the project that you were involved with?
Oh, gee, I can't say I ever saw the whole team in one place, but I mean, easily a few hundred.
Wow.
Yeah.
And
Lockheed Martin and the other partners. Yeah.
Can you tell us some of the other companies you've worked for, like Microsoft and?
Yeah, sure. So I've been doing software consulting work in Silicon Valley, or I did for more than 20 years. Worked for probably a dozen different companies in that time frame as a consultant. I've also been a full-time employee at Microsoft, and yeah, in the consulting business is kind of interesting because you work for a lot of small companies no one's ever heard of, and these little startups and so on that were so popular back then. But yeah.
Did you ever deal with Boeing at all?
I have been to Boeing, and I have had meetings at Boeing, but I've never actually worked for them. But I certainly know who they are. They're a big aerospace player.
I used to sell New Zealand products to them for the seating in the aeroplanes.
Ah, right.
So, nice company to deal with. So, some very high-profile companies that you've worked for. So now you're living in Nelson, New Zealand. Nelson. This is home.
Yep. Moved here 7 years ago. And love it.
Good. And can you tell us about any of the projects you're working on at the moment?
I'm working now for a company that's involved with developing software to protect personal data and security and privacy for kind of everyday information, identity information, that kind of thing.
But is the government still going to better get their little mitts on it?
Well, we hope not. We're going to try our best to make that not possible.
Okay. But do they have like legislation where they require an operator to be able to open it up so they can spy on it?
I don't, as far as I know, they don't.
Okay.
I mean, I think the rules have to do with exporting, the encryption technology and that sort of thing. And then, of course, if you're given a court order that you have to intervene, then if you can intervene, you have to intervene. But if you can't intervene, then you can't intervene.
Yeah.
So.
Well, Rick, thanks for talking with us today. We've got another program coming up this time next week on Issues, and it will be an extension of this very subject. And thanks for also talking about some of the special software to keep little ears away from listening. They say that the most government departments are not listening to us, except the spy agency. We'll take a short break.
For generations, Concrete and Metals Limited have been the trusted name in providing concrete materials and contracting services for all those large and small jobs, from landscaping to houses to driveways and right up to large subdivisions. Concrete and Metals, 99 King Edward Street, Motueka.
Waimea Telecommunications, specializing in free-to-air digital television, internet broadband connections, telephone and telecommunications systems. Call Julian Toon at Waimea Telecommunications on 544-4203.
Nestled in the Garden City of Christchurch is one of New Zealand's most beautiful and famous holiday parks, where we join the wildlife with a warm welcome to all visitors. The canopy of trees and gardens provide a tranquil setting amongst all the amenities, playgrounds, swimming and spa pools, and entertainment on a grand scale. This wonderful park offers the weary traveller a haven of quality. Low-cost cabins, motels, tourist flats, caravan, campervan and campsites. Meadow Park, located on Cranford Street near the main North Road, Christchurch.
The majority of information in our life comes to us through our vision. With only one set of eyes to last our lifetime, it's important that you look after them. For over 20 years, Vizique Harrington Eye Care has led the way in providing the Nelson Tasman region with professional eye care. Our team are committed to providing you and your family with the highest standard of eye care. As part of this commitment, at Vizique Harrington Eye Care, we recommend Crizal lenses. Crizal is a revolutionary lens which repels dust and fingerprints. This means it's easier to clean and stays cleaner longer. Visit us at our Nelson, Richmond practices and ask about our Crizal satisfaction guarantee.
Welcome back. You're watching Issues. We've been talking about space travel and space vehicles. Today we've been talking with Rick Kissing, and he wrote the software that helped guide one of the spacecraft to Mars to take one of the rovers to have a look around. So let's have a look at one of those vehicles in action.
The rover Spirit is 125 million miles from home. Whether it's alive or dead, no one knows. At NASA's Jet Propulsion Lab, mission controllers have lost contact with their $400 million robot.
The station is confirming that they're not seeing a signal at this time, but they're still looking for it.
Copy that. If you give us...
Spirit was about to make its first measurement of a Martian rock, when suddenly the signal dropped out.
As far as my displays are concerned, I can't see anything. They're not picking up any signal.
A few hours later, they heard 2 beeps in response to the question, "Are you alive?" That was yesterday. Now, they can't even get a beep.
We haven't gotten a beep yet.
So far, they have no idea what's wrong.
Sir, at this time, I have to report that we do not see any MAR data. Okay.
All they know is that they have a sick rover, a long way from home.
You know, when you get these pictures back, you really feel like you're there. It feels like a walk in a summer day in the desert. But suddenly, when a vehicle stops talking to you, the vast distance between Earth and Mars feels really, really apparent, and it just terrifies you that maybe that tenuous link that you thought was so strong suddenly is broken.
Until now, the mission had been a triumph for NASA and the Jet Propulsion Lab, where the rovers were built. For more than 2 weeks, everything had worked perfectly. Spirit was an international celebrity, in the news almost every day. With the risky airbag landing safely behind them, the most anxious moment came when it was time for Spirit to drive off the lander.
We've got the vehicle completely deployed, ready to go, and now we're going to be sending it off onto this big first step. To put it bluntly, to screw up that step would have been a tremendous disaster.
They would have preferred to drive off straight ahead, but part of the airbag was in the way. Rather than risk getting tangled up, they used the test rover in the Mars sandbox to practice a tricky move. A turn in place on the lander so they could drive off in another direction.
It's like your first child. The first time through, everyone was kids gloving it and nervous at every phase because, you know, the world was watching you. Spirit was tough. Spirit was a sleepless, tough time.
Charlie Tango _ Romeo 21906 decimal alpha decimal 00.
Finally, it was time for Spirit to take its first big step.
Is the most significant 3-meter drive in recorded history.
Setting on my mark. 3, 2, 1, mark.
We're essentially just pushing a button and sending it off on a 3-meter journey and then finding out later if it worked. Very, very stressful.
90 minutes later, Spirit sent back a picture of the empty nest. With 6 wheels on Martian dirt, the most dangerous phase of the mission was over. The time had come to start exploring Mars. This is what everyone had been waiting for. And then Spirit stop talking.
They did not see any sign of signal from the laser. We didn't see anything. Okay, copy that.
The next day, when we didn't get any communication down, there were people sitting there saying, oh my goodness, this thing might not ever work. And then all of a sudden, when no one was expecting it, it started sending down data.
Flight station reported that they're seeing signal at 143536 on all the downlink channels. Great news. Let's see if we can look up to it.
We got what appeared to be one of the messages that we really wanted to see. But as we went through it, and with the crowd of people around us, it became fairly obvious that it was just a really unfortunate piece of garbage data.
We're going to look at some more, but it doesn't look promising.
But even garbage is better than nothing.
I was thinking, at least it's trying. So now we have a chance.
Tracy Nielsen is the fault protection engineer. She helped design systems that put the rover in a safe mode when things go wrong.
What they do here at JPL is they build a lot of robustness, a lot of fault protection capability, a lot of ability to keep the vehicle alive into the hardware. And what that does is it buys time. It buys time for some very smart engineers to go through the data and figure out what the hell happened.
We're thinking there's a problem with the software, and so...
They have lots of theories, but until they get some real data from the rover, they can't diagnose the problem.
Get the same thing, so give us a minute.
Copy that. Just want to understand. Thank you.
There's a lot of pressure with get us the answers right now, and people 24 hours a day asking us what's going on, and we couldn't tell them anything.
An hour later, they try to get Spirit to talk again.
Copy that. 63.
Then it did start talking to us, and it was great. I mean, everything looked perfectly nominal. We were cheering, and then it sent the same data again a minute later, and then it sent the same data again. And then it sent the same data again. And then it sent the same data again. And we're like, oh, it's like Groundhog Day. No. And then the signal dropped out.
Just when Spirit seems to have lost its mind completely, it calls home again.
Fault monitors, 72 monitors.
And finally, there's some useful information. Spirit's computer has tried to reboot 66 times in the past 2 days. When a computer crashes on Earth, you can press the reset button and start over. But when Spirit crashes, there's no one there to press the button. So it's programmed to reboot itself. And that's what it's been doing, over and over for 2 days, without shutting down at night to conserve its batteries.
So when it's supposed to be asleep, the thing was awake for hours, thrashing around, doing we don't know what during the night. And the battery is getting, the power system is getting pulled down lower and lower and lower. The vehicle is not designed for some of the things that it was going through. They
send a command to shut down, but it doesn't work.
I wasn't even sure if we were going to make it. We didn't seem to be making progress in getting control of the rover, and if the battery just kept going down, we could have lost it.
As night approaches, the unhinged rover is still wide awake. The automatic fault protection should shut things down before the power system is damaged. But it may not work in this crippled condition. With the rover on the dark side of Mars, the next chance for contact is 19 hours away, if Spirit survives the night. Work continues at JPL, searching for a common thread that links all the problems they've seen.
Change the ball, how fast we're putting data in the pipe.
Everyone could use some sleep. They settle for pizza.
I went one day where I went 27 hours here at work. There's always one more thing to look up, one more thing to check. So even if you do go home, you can't really sleep.
Tracy spends this night working with the test rover, trying to reproduce Spirit's puzzling behavior, while the rest of the team pursues other leads. By morning, they have a suspect. The flash memory, Spirit's equivalent of a hard drive, where the computer stores data when the power is off.
And as it turned out, there was a way, which we'd used in test, to isolate flash memory and keep it out of the picture altogether.
Flight mission, your go.
Still not knowing if Spirit survived the night, they send the command to restart without the flash memory. Nothing happens. But there's a good reason. Spirit is asleep. The fault protection worked, pulling the plug during the night, probably saving the rover's life. Later, Spirit wakes up and receives the command.
Flight Ace, we've locked on telemetry 145414.
And it works.
We have partial control of the vehicle.
Even so, without the flash memory, Spirit can't do much. And they still don't know what's causing the problem.
We are a long way from being out of the woods. It's going to be quite a while before we go in science with this thing again, but we have got a way of talking to the vehicle now so that it responds appropriately. It has regained its sanity, and that's a good feeling.
And not a moment too soon. Opportunity will be landing on Mars in just a few hours. Saturday night, January 24th. It's showtime at JPL. At 8:59 p.m., Opportunity begins its plunge to the surface of Mars. Spirit's crisis was a blunt reminder of how quickly things can go bad. And landing is the most dangerous moment they face. A nerve-wracking 6 minutes of automated parachutes and airbags that must work perfectly to work at all.
If you go for that full emotional roller coaster ride, you're history. I mean, it is just emotionally too hard to take over and over and over again. Though this is an exciting ride, you know. If we get this vehicle down the surface of Mars, we'll be very, very, very happy.
The spacecraft is bouncing on the surface of Mars and rolling around. The antenna is pointed in many different orientations.
LCP, we see it on the LCP.
We're seeing it on the LCP.
The landing team is feeling especially good tonight. In the space of 3 weeks, they've beaten Mars twice.
There's actually 3 things we need to do here. 1, drinks. 2, take a picture. And 3, go together to the press conference.
For 3 years, delivering the rovers safely to Mars has been the focus of their lives. Now their role in the mission is over. Almost. The press room is already packed with reporters waiting to hear from NASA's top officials. But this is an irresistible force. These engineers are now the world's leading experts at landing on Mars. Many of them are already at work on future missions. But this one will be hard to top.
All of us on the EDL team acknowledge that this is the greatest experience of our professional lives. So there's a lot of separation anxiety. That's what we're talking about. You know, how can anything match this?
To the Mars Exploration Rover team, the best in the world.
Spacecraft have been visiting Mars for more than 30 years. From orbit, they've seen ancient floodplains, dried up lake beds and river channels. Strong evidence that this now cold, dry planet was once bathed in liquid water, the essential ingredient of life. Recently, scientists have found life on Earth in places they never thought possible before. Miles deep underground, beneath Antarctic ice, even in boiling water by deep-sea volcanoes, living on the chemical energy of sulfur instead of sunlight. Wherever they look, if there's liquid water, there's life. So if early Mars had water, perhaps it had life as well. But so far, attempts to find it have failed. And so have attempts to find proof that Mars really was wet.
The evidence that we should find, we don't find. We don't find the minerals that would suggest that there was lots of water around on Mars long ago. However, we do find the channels. So there's a contradiction. There's a question, what's going on this planet which has part of the evidence, but not all of the evidence?
To find the answer, Spirit and Opportunity will explore sites that look like they once had water and try to prove it on the ground. For Spirit, the science team chose Gusev Crater, which they suspect was once a huge lake fed by a channel the size of Grand Canyon. And on the other side of Mars, they chose Meridiani Planum, where an orbiter recently detected a mineral called hematite, which sometimes forms in contact with water. This is where Opportunity just landed.
That's the first time in the history of planetary exploration that a chemical signature on a surface of a planet of the type we were looking for, related potentially to water, was staring at us.
Now look at this one.
Look at this!
The first pictures are stunning. Just a few feet away from the lander is an exposure of bedrock, the first ever seen on Mars.
Holy smokes. I'm sorry, I'm just blown away by this.
Bedrock is the holy grail of geologists, a record of ancient environments carved in stone.
This is the sweetest spot I've ever seen. That outcrop in the distance is just out of this world. I can't wait to get there. I got nothing else to say, I just want to look.
When the full image arrives, they realize that Opportunity hit a cosmic hole-in-one, landing in a shallow crater.
We got lucky. I mean, we just got damn lucky. You know, Tiger Woods couldn't do this. We just went right into it. And so we're lying in the bottom of this crater, and the beauty of that is that the crater walls expose materials that we wouldn't otherwise see. I mean, there's this wonderful rock outcrop here. And if we were out driving on the plains, this stuff could be a meter beneath our wheels, and we'd never know it was there. Instead, because we fell in this crater, there it is.
The science team has been planning, rehearsing, and dreaming about this for years. Led by principal investigator Steve Squires, this all-star collection of geologists and planetary scientists is about to start exploring Mars in a way that's never been done before. Right away, they're confronted with something new. The rock seems to have fine layers running through it. Layers suggest the possibility that it's sedimentary rock, formed by the accumulation of sand or mud, perhaps on the floor of an ancient sea. Or it may just be hardened layers of volcanic ash. Volcanoes covered much of Mars in lava and ash billions of years ago. And until now, scientists have seen little evidence of anything else.
Most of the rock on Mars is volcanic lava flow. This is something else. This is an unusual Martian rock, at least compared to what we've seen everywhere else. The fact that these rocks are layered says that one possible origin for these is that they were laid down in liquid water. We do not know what's going on here, but the beauty of it is we have preserved in front of us a record that will answer that, and we have on our rover a toolkit of gizmos that will tell us that answer.
A week later, Opportunity rolls off the lander. They look for the hematite, the water-related mineral that drew them here in the first place. The infrared spectrometer, called Minites, can identify minerals according to how they absorb and radiate heat. A false color image shows lots of hematite in the red and orange areas, and very little where it's blue and green. The areas with the least are where the airbags left their imprints. Then, with the microscopic imager on the robotic arm, they take a series of extreme close-ups of the soil and find another puzzle. Tiny spheres the size of BBs litter the ground. A short drive forward brings the rover close to the outcrop. Another image, with the color tweaked to distinguish different materials, reveals more spheres. And more close-ups show them eroding out of the rock.
Embedded in this outcrop, like blueberries in a muffin, are these little spherical things. And they're really, really round, and we're trying to figure out what they are.
Just a few days into the mission, Opportunity has turned up evidence of something. But exactly what remains to be seen.
It's like a mystery novel, okay? You know, you read a mystery novel and you get fed these clues. And we're trying to piece these clues together. And right now we got a partial story, and it's, I don't know how it's going to come out.
Spirit is ready to get back in the game. The engineers found that the problem was simply too many old files in the flash memory.
I'm sure Opportunity is thankful to Spirit for finding this problem, because they would have been there in about a week, you know, and we would have had 2 rovers with, 15 stalls of debug.
When they're sure that nothing else is wrong, they delete the old files, pronounce Spirit cured, and chalk it up to growing pains.
The Spirit rover always seems to have been a bit of the trouble child. And it was just when all the attention was shifting away from Spirit to Opportunity, because Opportunity was going to land, it almost seemed like, a sibling that was trying to get attention back to itself.
But along with the good news comes the realization that Spirit was not as fortunate as Opportunity in its landing site. If this was once the bottom of a lake, geologists would expect to find the kinds of rocks and minerals that form in a wet environment. They sample a boulder and the soil near the landing site. But it's all volcanic and shows no sign of ever having been wet. The evidence they're looking for may have been buried, or it may have eroded away, or it may never have been there at all.
The rocks that we have analyzed appear to be basalts, the most common type of lava. And as a person who is really interested in lavas, this is fine with me. But it's a disappointment in a way for the mission, because we are after evidence that this really was a lake bed.
Maybe they can some kind of thing.
Natalie Cabrol was one of the first to suggest, 15 years ago, that Gusev was once a lake. And she fought hard for its selection as one of the 2 landing sites.
I think we're on the right track. It's just like the evidence is going to pop out like it did in Meridiani, because we happen to land in front of an outcrop.
If the evidence of water has been buried, a good place to find it might be in the exposed walls of a small crater in the floor of Gusev. From Spirit's landing site, it's 300 meters to a crater they call Bonneville.
Bonneville might give us an interesting insight on what's underneath our feet.
It will take weeks to get there, but it's the best chance they have.
We're kind of grasping at straws here, looking for the right stuff. It's a tougher site, it's a harder site to love, but but it's what Mars has given us. So.
Back at Meridiani, Opportunity's team is ecstatic. They've spent the past week traversing the outcrop, creating a close-up photo mosaic. Now they're selecting targets for closer study.
I think we're all in Mars Geology 101 here. It's an experience where we look at the evidence and say, well, what could this possibly be? This is an alien planet, and we don't know what we're going to see when we get down close and personal with this rock. With each picture that comes down, there's really an expectation that you just might break the whole thing open.
If this outcrop was ever exposed to liquid water, there will be clues in the chemistry of the rock. And that's what Opportunity is looking for. The rovers have 2 spectrometers on the robotic arm. One can identify minerals containing iron. The other sees chemical elements. Both work by bombarding the target with radiation and reading the signal of what bounces back. Every element and every mineral has a unique signature. So far, the instruments have seen a lot of sulfur, a common chemical element in volcanic gas. If the gas mixes with water, it can make sulfuric acid, and that can react with certain rocks to produce mineral salts called sulfates. A lot of sulfates in this rock would be evidence of water. But the sulfur seen by the instruments may be just a thin coating on the surface. The only way to tell for sure what the rock is made of is to get a clean look inside. And the rovers have a special tool for that purpose, the rock abrasion tool, or RAT. But the man in charge of the RAT is worried.
I thought that before landing we had roughly been able to approximate anything that Mars was going to throw at us. Of course, what I neglected to think about was a rock that would be spitting out blueberries. What we're afraid of happening is that we're going to dislodge one of the spherules, and that it's going to be like a pinball machine between the RAT and the surface of the rock. And this could be something that causes us some problems. Oh my God.
Squires thinks they're on to something big.
But what are we dealing with here? This rock.
Steve Gorovan's team spent years developing the RAT.
This does not look volcanic. This is not basalt.
There's not too many other things left.
Now the mission is riding on it.
Well, we're going to get to the bottom of it, so...
Yeah, exactly.
Literally.
And it's you who got to do it. Okay.
I will.
Well, that's Issues for another week. I'd like to thank my good friend Rick Kissing for his contribution today. If you have any questions or comments you'd like to make about the program, you are very welcome to email us at issues@7-media.net. Next week we'll have part 2 of this program.
Hi, my name's Ian Mortimer. Mortimer Auto Upholstery is your one-stop shop for all your upholstery needs. We do car and boat interiors, boat canopies, ute tonneau covers, canvas and PVC fabrication. Call in and see us in Oxford Mews, 72 Oxford Street, Richmond.
O2B Healthy.
Lifestyle, diet and exercise, complemented with quality supplements, can provide you the insurance vital for your natural health and well-being. With over 10 years professional experience making some of New Zealand's most trusted nutritional supplement brands, visit the O2B Healthy factory outlet in Wakatu Industrial Estate. Over 200 supplements to choose from, free on-site parking, no middleman.
O2B Healthy. Caring for you naturally.
If you have a complaint about any program on Mainland TV, you can write to Mainland Broadcasting, Box 595 Nelson, or contact the Broadcasting Standards Authority.
Nelson Tire Center. Great prices, great service.
Buy your own Bryford trailer, all types, all sizes. See Colin Douglas for your tires and batteries.